Okay, welcome to the Davis R users group. I'm going to talk a little bit today about automation in R using apply and lapply and writing your own functions. Mavanvi, can you confirm that we are broadcasting to the internet through the Google Hangout? Somebody just drop a comment in there letting me know that you can hear me. Can someone in the room go to the page that I linked to in the message yesterday and see if we are in fact broadcasting? Yeah? Okay, great. Okay, so I'd love for this to be interactive. I have a few ideas of what I'm going to go through, but if you have questions at any point, feel free to interrupt me. I'm going to be coding live so that I can answer questions. And then if you have, I invited particular tasks or problems. So if you have particular questions or if you have something that you've been trying to do, I'm happy to work that in as well. If you would like to follow along on your computer, I have this little trick that I use. So I'm going to save my file as I go, which will save live through Dropbox. And if you want to follow along, you can pull it up in your browser through this link, tinyurl.com/drugauto, so drugauto. And that should, let me know, does that get you this script?
Yes.
Excellent. Okay, with that, by the way of prelude then, let's make this a little bit bigger. Load a couple of our handy libraries. And I thought we'd start with apply. So when I first started learning R, I first started coming to the R users group, for like 3 quarters, I asked Noam for a talk on how to do the things that I know how to do in Excel in R, right? Like things like drag down a column to do some operation relative to another column or that kind of thing. And apply is the function to do that. It took me a long time to figure it out, but I thought we'd start there. So I'm making a matrix of some simulated data of how much 20 hypothetical people sleep on each of 7 days of the week. So here's what that looks like, right? We've got 20 people in rows across 7 days of the week. And what apply allows us to do, let's take a look, is to go over the margins, which is a fancy word for the rows or columns, or in a higher dimensional array, the 3rd or 4th dimensions, and do some function on the rows or the columns, or both, on each cell of the thing. So X is our thing, so D is our matrix. And then the margin, so we use the square brackets to delineate margins, right? So if I do like this, that gives us the first row. Do this, it gives us the 15th row. So this thing before the comma, that's the first margin. And if I did this, that gives us the second column. The column is the second margin. So if I wanted to go over, let's say go over the columns of this, I'll go over the second margin, right? Rows go before the column, comma, they're the first margin. Columns go after the comma, they're the second margin. So margin equals 2, I'm going over the columns, and then I can do whatever function I want on that. So it's going to pull out each column of this data frame or this matrix and do some function on that column. So let's have it take the mean. So we could have done D1 mean, and that would give us the mean for Monday. We could do D2 to get the mean on Tuesday. This goes through and gives us the mean on each of the days. Now, we can build up functions of arbitrary complexity. So mean returns that 1 value for each. We can do range, which returns 2 values for each. That gives us the minimum and the maximum. And then it coerces the results into a matrix. We can also use this ... argument to apply. to supply additional arguments to the function fun. So we're putting so I should name these things. So x is our object, it's D. Our margin is 2, and our function is range. If I want to apply, I want to do something a little more complicated. Let's do quantile, which I think by default returns the 0, 25, 50, 75, and 100th percentile of each column. If I want to specify that I want, say, the 95% interval, so I can do that for one column like this, right? So if I did quantile of the first column, and then second argument to quantile, this probs, lets me do like this to get the 95% interval. So I can do the same thing within apply, like this. So the function is quantile, and then the ... is that second argument to the function quantile. Oh, that did not work. So is it clear how this is working? Right? It's taking this matrix D, splitting it into the 7 columns, and then for each of those 7 columns, it's calling quantile, and the first argument is the column. And then we supply additional arguments through probs.
Or through whatever the original function, the argument name is, right?
That's what probs is.
Yeah,
yeah it has to be through the original function's argument. That's what I just messed up.
So quantile took like 5 arguments. You could just keep listing those out.
Yeah, and I think you would put them in a list in that case. So what else does quantile take? It was true. Maybe those don't go in a list. Because ... will suck up any number of arguments, so they actually go separately. But so anything after fun, so the first 3 arguments to apply are the data frame or the matrix or whatever, the function, the margin, the function, and then anything else after that is an argument to the function, not to apply. If we wanted to do something more complex than that, we can use this kind of construct. So let's go to D, to, and then we can say function of x. What that does is it says take each column in D and call it x. And then I can do whatever I want with each of those x's. So the simplest case, we can just say return x, right? So that goes through, pulls out each column, and returns each column. Just like before, we could say do the mean of x. Or we can say, x squared equals the mean of x. Average equals x squared, and then equals mean of x, and then if we wanted the square of the average, we can do like that. So we can build up functions of arbitrary complexity, and these curly brackets allow us to have multiple lines within this function, right? But so within these curly brackets, x is going to refer to the columns of D, or whatever the thing is that we're applying over. We can do likewise over rows. So if we set the margin equal to 1 and call for the mean, then we get the average across each row of the data frame. And we can also go over multiple margins at the same time. So if we go over margins 1 and 2, then it will go to each cell in the matrix, right? It'll go over the rows and the columns and return something for each cell. So let's say we want to know if each person is sleeping more than 8 hours a night. We go function of x is x greater than 8. And then we get back a matrix of the same shape as the original one, and it's tested each cell for whether this is true. And here we could have simply done this, but that's what these curly brackets are for, so that we can do things more complex that we couldn't do with this simple vectorized notation. So we can say sleep more than 8 equals is x greater than 8. And then if sleep more than 8, if else sleep more than 8, you sleep a lot. You must be tired. Then we get back again a matrix of the same shape, but we're still going over each cell and doing, we can do whatever, right? We could use these as coefficients in a model. We could use these as whatever. And we'll get into some more complex applications where it actually makes sense to use these functions. One thing to note, and this is sort of what makes RR, one of the things that makes RR, is that apply outputs a new matrix, and it has the same dimensions as D, our input matrix, if we go over 1 and 2. If we go over 1, it gives us back the number of rows. If we go over 2, it gives us back the number of columns. It's never going to modify D, right? It's always going to give us back a new thing. And then we can save that to a new object. Right? So now we have in our environment, we have our original matrix D and a new matrix of tired people. This will never modify D. Any questions about that? Lists. Lists are a data structure in R that allow for the holding of arbitrarily complex data. So anything can be part of a list. So here I'm going to make a list that is, well, actually, let's do this. Okay, so I have this new object in my environment, my list. It has 3 things in it. If we just return it, the first thing is just this variable named A, which is a single number. The second thing is a vector called B, which is 3 numbers. And then the third thing, C, is another list with 2 elements in it. So C has then a thing called 1 letter, which is A, and a thing called many letters, which is a vector of letters A through E. We access elements of a list using the double bracket notation. So if we want the first thing in the list, do like that. If we want that third thing, the list within the list, we do like that. So notice this has given us back a list. And then we could go into that and say, give me the second one of those. And then we get this character vector called many letters. Right? If you only use a single bracket, so my list 1 returned the thing that was in this first element, this number 1, right? This is just a number. If instead we use a single bracket always returns a list. Okay. Yeah.
Sorry, what does
Please.
double bracket do?
So a double bracket pulls the thing out of so the way I've heard it metaphorized before is train cars. And a double bracket pulls, so if you have a list and that's a train, right? And each train car is an element. The double bracket takes the thing out of the car and throws it on the ground. The single bracket takes that train car and just extracts it with the contents and the car itself. Here, I think I have this up. Here's a tweet from Hadley Wickham trying to explain this concept. So if X is our list, right, it's got all these individual things in it. Use the single bracket to get that first thing out, it's still in the shaker. It's still in its container, right? If we use the double brackets, then it pulls that thing out of the container, and we just have the packet, right? And then if you use the double bracket again, pull the things out of there.
So this is like if you wanted to remove something and then use that value to do something. Like if you wanted to reassign that to like a variable that you then wanted to do further analyses on, like what?
So in most cases, you'll want to use the double bracket. If you want to do something with that object from the list,
I see.
you'll want it as a data frame or as a vector.
Right.
So you want to pull it out with the
So if
double
you only
bracket.
use the single bracket, that means that it would only tell you what that value is, but you couldn't like reassign it, or you have to like copy and paste it or something.
Well, you can still use it. It's just going to be buried in a list.
Okay.
And the reason for this, so I can pull out the first two things. What is it, my list? 1:2 just gives us 1 and 2. So I can pull out the first two things from the list like this. If I try to use double brackets here, that won't work. Because then I'm trying to take the thing out of two train cars and throw it on the ground. And R's like, well, I need those cars to keep this organized. Right. So all that's fine. Now let's use lapply to start to automate it. So lapply, just like apply, I probably should have started with lapply. I think in some ways it's actually simpler. Lapply is going to go over each element in the list and do some function. So we can see that in the help file for lapply. Right. Lapply takes some object X, does some function to it, and then if we want, we can pass additional arguments to the function. So let's lapply over my list. And
Stands for list.
yes, L stands for list.
And apply was only for data frame and arrays, or?
Yeah, array-like things. So arrays, matrices, and data frames.
Okay.
Yeah,
Gotcha.
won't work on lists. So let's just ask R through lapply, go through each element in my list and tell us what kind of object that is. Okay, so remember what my list looked like. If this first one is this one number, the second one is this vector of numbers, which it's coerced into integer form, and then the third thing was itself a list, right? So that's what it spit out. We could, of course, since that third element is a list, go over the two elements in that list and ask it what those things are. Yeah, let's do something more interesting. Let's talk baseball. So, I don't know how to say this, Le Mans package provides a whole bunch of, it's a complete set of Major League Baseball statistics dating back to like the late 19th century. So I thought we'd work with that for fun. If you want to follow along, go ahead. The code there is complete. It has a whole bunch of different data tables. We're going to pull out the player salaries and the players' batting statistics and see if we can predict how well they hit from their salaries. And we'll do this with some automation so that we don't have to do things individually, but we can wrap it all up in these lists and go over a whole bunch of different models at the same time. As an aside, we're going to put everything in 2016 dollars. Here's what the salaries look like. baseball players make a lot of money. Where shall we start? Let's well, let's look at what that looks like. So here's our data frame. We have adjusted salary as a column, and we have all kinds of batting statistics, right? And up here we have years, players, teams, league. So let's build some models. So of course, like, first let's start outside of the context of a list and say model equals linear model of, let's do batting average as a function of adjusted salary. Okay, that's fine. There's a linear model. No surprise, a player's salary is positively associated with their batting average, right? Let's say we want to run a bunch of models. Rather than doing this, so we could like copy this and then paste it, and then we could say, all right, does this vary by league? Look at that, it does. Players in the National League make less than players in the American League. But we don't want to copy and paste like that. We can do better. So let's make some formulas. Make a list here. So F1 equals, so in the linear model call, the first thing to LM is an object of type formula. That's what this BA tilde adjusted salary is. So we can write those out separately, and then we can loop over those formula using lapply to generate a whole bunch of models. So we'll do that one. Batting average as a function of salary. Batting average as a function of, let's do it the other way. Let's predict salary as a function of batting statistics. Do home runs, and then let's do a model with the interaction of batting average and home runs. Okay. So there's our list of formulas. Now we can lapply over the formulas. The function is, so remember in lapply, the first thing is x, the thing we're looping over. The second thing is the function. Here that's lm. And then the additional argument that we need to specify is the data frame, which is bb. Models. And there's what we get. There are 3 models. And now we might want to look at those. So now, of course, we can lapply over our models and get a summary back. And then we get summaries for our 3 models. Or, so demonstrating the use of that arbitrary complexity, we could do something like this. By doing this model's function of model, now within this lapply loop, the variable model is going to take on each of those models, right? That's what this line 90 is doing. It's saying, take each of the entries in models, call that model, and do this stuff between the curly brackets. The way I like to do when I'm writing these is to save the first object in the list to model. So the first time lapply goes through this, it's going to effectively do this, right? It's going to set model to the first thing in models. So I'm going to write my functions using that. and then we'll delete that to get it out of the way. So let's do this. Let's do model I was sure there was something of extra complexity to do here, but I'm not sure what it is now. Let's do this. We'll take the coefs and save those to one object, and we'll take the p-values. That's not going to work. In any case, you can do things of arbitrary complexity between the curly brackets. We'll demonstrate in a minute. Please.
How come when you put those formulas up there, you don't have to specify? You could just use those columns right out of it.
Yeah, so a formula is a particular kind of object in R, and so it's just seeing that. And then here in the lapply call, I'm providing the data frame.
Okay, cool.
Yeah. So you could, and if there's time and interest, we'll get to this. We could have a whole bunch of different data sets in different data frames, and we could call some modeling function with the same formula over the different data sets.
Yeah. That lapply thing you just wrote, is it not going to rewrite coefs at each iteration?
It is. That's exactly what it's going to do. So it's going to spit out then the coefs for each model.
Okay, but you're not actually saving something
right, because
outside of the function.
lapply never writes, unless you go to great lengths to make it do this, it will never overwrite what you've provided as input. Which is.
But I mean to save, see, because that's where I've had trouble or just ended up copying and pasting when, like, maybe I want m1.coefs, m2.coefs to actually save them as objects, or save the model summary as an object to look at later or do something with.
Mm-hmm.
I mean, I guess you could you just save this thing, this output, and then split it up, or?
Sure. So we can save coefs like this.
3 vectors out of this, or 3, yeah, lists out of this.
So then we can take coefs 1, and there's our coefficients for the first one. One thing I often find useful, let's see, oh, those are named. Yeah, does that answer your question?
Not really, but keep going.
Well, no, let's get into it. I think that's more useful.
So it's like, okay, so for instance, if I have a, I mean, I've typically tried to do this with for loops, but the problem is assignment to make the object available outside of the loop.
So for loops behave really differently than apply loops. For loops, you can do assignment within a for loop. When you're in a for loop, you're still operating in the global environment or whatever environment you're in outside of the for loop.
Mm-hmm.
When you do an lapply, you're creating a new universe, and you only modify things within that universe in R. For loops allow you to modify things in the bigger universe, the global environment.
Yeah, I guess it just gets messy. So for instance, if I have 5, say I have 5 models fit, and I want to do save like some summary output, as a data frame table, whatever it would be, calculate confidence intervals, whatever. I have a list of 3 or 4 things that I'm doing. I'm going to do the same thing for model 1 as I'm going to do for 2, 3, 4, 5. But then I want them saved as objects. Like I want m1.summary, m1.confidence intervals, or whatever it is. I guess you have to do like because for instance, to just create the name of the object you want it to be saved as, it would be, you want to save you need to like paste together the M1 as a character vector with like the dot summary or dot whatever.
So this is great. This is what I want to demo. It depends a little bit what you mean by save, right? Do you mean like write to your hard drive, or do you mean just make available in your R session?
In your environment, yeah.
Yeah. Okay. Great. So let's do this. Let's name these a little more descriptively. We'll call this just batting average, and home run, and we'll call this interaction. Okay. Generate our models. Now, I'll apply over our models. Let's get coefs. We'll get summary tables equals summary of model. Here's one useful trick, Evan. If we do sequence along models, the sequence along just gives you a number for each thing in the argument to sequence along. So here we have 3 models, so this just gives us 1, 2, 3. Doesn't seem that useful, but wait. Then what we do is we call models. I'm going to change this model to I. Then, so now each time we go through another loop in here, instead of going through each item in models, we're going to go through 1, 2, 3, but then we can get each item in models using this. And the advantage of that is that we can get the names of our models like that. Right, so now for demonstration purposes, let's say when I equals 1, model names will take this value, coefficients will take these values. We can do whatever we want. Another thing to note about lapply is that it will always return, unless you tell it explicitly otherwise, it will always return the last thing that you do inside the loop. So if I say here, A, it's gonna do all these calculations, but then it's gonna throw them away and just return hey for each iteration of the loop. So if instead we want these objects, we can put them in a list and output them, right? So we can say name equals model names, coefs equals coefs, and summary table equals summary. And we get a list of lists, right? Because we get, for each model that we send to lapply, we get a list of 3 things back. And we could, again, we can do things of arbitrary complexity. And I'm struggling a little bit to come up with useful examples, but we could say, we could assign an attribute to this. So let's say we'll call this the return list. And then we could set the attribute of return list, which is like a description, to paste 0. The model name is model names. So suppose we don't want these coefficients in this list. Instead, we want them as an attribute. That'll do this. So let's go through this for the first item in the list, and then we'll run the whole loop. So do all these things, they work as before. Here's our return list, right? It's got 2 objects. The first is the coefficients. The second is this summary table. And then this last line will set the attributes of that table. Maybe. Not sure what just happened. So have you guys seen attributes before? So attributes are awesome. They're super useful, and I think underused. So an attribute is a way to attach something to an object in R without it really being a part of the object. So I use this all the time. If, for example, so in the ergon framework, there's a particular subparameter that we have to set for values of for these big models, and because of the way it's coded, the value of this parameter doesn't end up in the models. But I always want to know what I set that value to in the model, and it gets lost when I save it as an RDS or an RDA or whatever. So I set the attribute of that model. I make an attribute of that model called GWD, and then give that the value of whatever I used in the model. That was probably not the clearest description. I apologize.
It's a tag, basically.
It's a tag, exactly. So here, this function is saying, adder is a function. It's saying, on this object return list, create an attribute called description, and then I'm setting the value of description to be this. Let's do a simpler.
What is that?
Sorry, I'll describe that to you. It's just pasting two objects together with no space in between. So normally paste inserts a space, paste 0 doesn't. X equals 2. Okay, that's what X looks like. Attributes of X, there are none. If I say attribute of X, what it is, equals a number, now when I return X, it has this attribute on it. The name of the attribute is what it is, the value is a number, but I can do things like X squared, and that attribute doesn't get in the way, right? So we often have objects of a certain data type, and we want to be able to, say it's numeric data. We want to be able to do stuff with that numeric data, but we might want to append a little bit of text to it. So the attributes let us get that text outside of the data itself, but still keep it attached to the object.
Why would that be better than just adding a new row to the data frame with whatever text or something like that? Like, what does that do?
Because then, so if, for example, back up here, so this is all numeric, right? And that allows us to apply over the columns and take the range. If we made, if we added another column, I don't work with matrices that much. I don't think it's going to let me do that, is it? Find D and repeat text. Right, so look what happens there. If we put that in as another column, then all of a sudden R isn't seeing these things as numbers anymore. It's seeing them as characters. And so now we're not going to be able, now if we try to do this again.
Or if you had a data frame and they were numbers and characters, you're still not going to be able to take like the range of, or it's going to be like, you're going to get a weird answer.
Yeah.
Range is a bad example. But.
So now that changes the whole matrix. So.
Right, exactly.
Yeah.
So rather than changing the whole matrix,
yeah.
Put it on as an attribute, and then it's separate.
Is it then accessible though in any way? Let's say you wanted to like create a graph and then have it be categorized by the attribute that you named it.
Totally. So.
So it's sort of like there but not there in a way.
Yeah, absolutely. So we could, let's see here. If we did in here, function of f, lm of f comma bb. Okay, so this is the same. This is just building our models like before, right? But let's break this out. Model is that, and then set the attribute of the model called the formula. Oh, shoot. Now in order to, I want to access the names of, oh no, this is fine. As character So now we've got our models, and each has this attribute. Nope. I didn't return the model. So because I didn't have this line here, like I said, lapply returns the last line inside the loop. So it was just returning the attribute. Instead, I want it to return them. So I want to set the attribute on this line, and then I want to have it return the models, which will have the attribute attached to them. Here are our three models. Did they get those attributes attached to them? Yes. So this first model has, so LM attaches some attributes by default, right? So it attached to this model all of the names as attributes. It attached the class as an attribute, and then we attached the formula. So now, if I wanted to say, let's say plot the coefficients of a model, right? That's sometimes we might want to do this over 100 different models and then plot the coefficients and see how they vary. So let's then apply over models, function of M. Let's do this. Coef of M text, attribute of M. Paste that together. Let's see. So forgive the ridiculousness of the graph and the ugliness of it as well. So we've made a plot of the histogram of the coefficient. I'm not saying this is a good idea, or this is useful, but you can imagine doing this in a useful way, right? You run a whole bunch of models, you want to see how the coefficients compare. And you want to title each graph with some attribute of the models that generated those coefficients. You can attach those attributes as attributes and then use them to annotate your graph. Or you could even save the files, right? So you could say, so lapply over models, attribute, formula, so that'll return like that. Piece those together. Actually, let's take just the second and the third. So now we have some text that we could use to potentially save these models to disk, and we could do that as part of the automation, right? So we could call these the names, and then we could lapply over, well, we'll just do this 1 through 3 function of I, and then we can save RDS, and the object will be models I, and the file will be where I am. I'm on my desktop, that's fine. So then the file will be names I. And then if I, how do you show your desktop? Nope. What is my working directory? Here are those three models, and the names of the files came from those attributes, right? So that was a really long way to get to here, but I never typed these file names, right? I extracted the model formulas that were used to generate the models and used those to name the files, right? So we could potentially do something like, let's do this. This will maybe demonstrate the use. So the names of, so there's our column names. Let's run a regression of salary on each of those things, right? And then we'll save each of those models to disk, and we'll do some stuff with the models. So we'll just lapply right over those names. Function of the variable. Oh, except not salary. Do that.
Vested salary.
I'm going to loop over each variable in the data frame, except for the one that we're using as a dependent variable. Each one will become var, and then we'll call this model equals lm of adjusted salary as a function of the variable. And the data is EB.
You need it after the second parenthesis.
No, I think it's a parsing thing. Okay, we're not actually going to do this. Sorry, guys. Let's see.
Ask a quick question.
Please do.
So you had said before when you just use the lapply setup that it'll return the last thing in that code snippet there. But if you assign, say, everything like 117 down to 24,
Yeah.
something else, it does get everything, right?
No.
It doesn't?
No, it doesn't. So so let's do this. Lapply 1 through 5, function of a number. Square equals number squared. Cube equals number to the cube. And then use case 0 again. Number is give this back the numbers, but square and cube disappear, right? They don't show up in my environment. They're just gone.
And you could call that whole thing like some arbitrary, give it like an object. Still won't get it.
Still is just going to pull those last lines out. We could do this. Square is this \n just creates a new line. Its cube is cube. Seriously? Put a new line at the beginning too. All right. And there you go.
Cool.
Okay. Okay.
So they're not gone, it just doesn't show you.
They're gone as soon as you run the loop. No, they're not stored anywhere. Yeah. Take it easy. Any other questions I can answer? I'm sorry that was not better organized.
Well, one thing you would want to do in that situation, so when you pulled the coefficients together, you went to all of the models, pulled the coefficients out, put them in one figure.
Mm-hmm.
One thing you'd want to do, say, would be for each model, look at the residuals against the fitted values.
Totally.
In a scatter plot.
So,
and if you want to get really fancy, you have to say 50 models, you might want a diagonal matrix scatter plots to kind of eyeball.
totally.
Throw out the bad ones.
So this is where I wanted to go, Neil. So let's just do it. So lapply. Let me remind myself what we have in models. Good, we have those three things. So let's do some predictions, right? So forward. I think we can just do this. So that makes a prediction for each row in the original data set. So I believe that's giving us back a list of 3 vectors, a set of predictions for each model. One of the things that I really wanted to show, and I'll go ahead and do it now. Actually, let's make this a little bit more manageable. So let's see, what did we predict on? We predicted on batting average and home runs. So let's make a data frame to predict for some counterfactual batting averages and home runs. I'm going to use expand grid. So expand grid, let me demo expand grid first. I'm going to try to get you your money's worth in the next 5 minutes. I really am. Expand grid takes all of the arguments to it and puts together each combination of them in rows of a data frame. So if we do expand grid 1 through 5 and the first 3 letters, it'll give us back a data frame with each combination of those numbers and letters. So here, let's do batting average equals a sequence from 0.2 to 0.35 by 0.1, and home run equals a sequence from 0 to, what's the record now? 74.
You mean 0.1 or 0.01?
I mean 0.01, thank you, Neil. Okay, so that's going to be, actually that's going to be bigger than I wanted. Let's keep this more manageable just so that it's visible. And obviously you could make it bigger, but let's do someone with 20 home runs, 40 home runs, and 75 home runs. There's what our data frame looks like. Now let's predict salaries for each of those players. So do it for one model like this. Data equals pred df. There are predictions. So it is a vector, so we could attach that to our data frame, right? We could say pred df is salaries equals that. And then our data frame looks like that. But we want to do this for a whole bunch of models, right? So let's do it for our 3 models.
It's not enough for somebody being 75 rounds.
They're worth more than that.
Let's repeat it.
It is. Why is it repeating? That's way too involved of a question. It's because I used this first model, and it only has batting average as a predictor. So it's not considering the number of home runs. So that's why that manager has undervalued the number of home runs. Okay, let's reset our pred data frame. Oh, I already did that. And now we'll lapply over our models. And then just like before, so just like we did here, predict models 1, new data equals pred df. Predict now with each model in this models list. And the new data is pred df. And now we have a list of 3 predictions. I'm guessing that if you did this, you would want those as columns on that data frame, right? Here's one of the idioms that I really wanted to demonstrate because it's super useful, is to be able to column bind or row bind over a whole bunch of things that are in a list. And to do that, we use do call cbind over preds. So you've all seen cbind before, right? It'll take these 3 vectors and column bind them together. Do call says take this function cbind and call it with each thing in preds as an argument. So this is same as cbind preds 1, preds 2, preds 3. And I'll show you that they're the same, right? Except for the details of the name. So let's take this. Oh, okay, great. So now let's open this up and attach it. So some curly brackets. How do I want to do this? I probably don't want to do it this way. Let's just cbind the pred BF and the preds, and we'll call that double D. And then we have our predictions from our 3 different models titled with each model.
So did that use the do call at all?
Yeah. So, oh,
Yeah, because you never saved the do call as a.
get out of here. Can you really just do that? But you had to do call cbind it.
Spread is still going to be a list, right?
It is, and if you just give it the list, then it's not column binding it like we would expect it to. But I think because this pred df was the first argument, it's saying, hey, this is a data frame, work on that structure. So it's doing some coercion. Tend to rbind thing, do call rbind more often. So you do a bunch of calculations and you end up with a whole bunch of different lists, a whole bunch of different coefficients, then we can row bind them together. And that do call rbind is quite useful. And then we could do some plotting, right? So then we could say apply over the name. Well, I suppose the way I would actually do this is in the Hadley verse. But we could, just to demonstrate it, we could apply over 3 to 5, function of the column, plot PD call as a function of TD, well, be consistent like that. This is a terrible example, but then we generate 3 data frames from that. We could, of course, together, and we could decorate like I was demonstrating before. Um,
That works. Then again, like you were explaining how it just returns the last thing.
yeah, because without getting into too much of the details, mtext is special. It's not, you can't just call mtext out of the blue. It's called on the plot.
So it's like a legend.
Exactly. Yeah, exactly. So in our context, one thing I do a lot is simulate networks over a range of parameter values, and then loop over those simulations and plot the networks, calculate some summary statistics and plot those. And that's super useful to automate. What else can we do? Anything else that would be useful? Let me demo one more thing that I do think is useful. So we don't really have time to go through it all, but I was going to have folks download this data and then show how to read a whole bunch of data files. But I'll just demo it on my machine. So list files list the files in some directory, perhaps that match some pattern. I'm going to go into Dropbox, teaching. This is that R bootcamp that I taught last summer. And then I think in day 4, data. Nope. What I have in here is housing prices organized by zip code for the Bay Area. And each of these, this data came such that each zip code was written in its own CSV file. So I have 314 different CSVs, and I want to pull all of this together and do something with it. List files lists all those files. And then I can do like this, lapply over file names, read.csv. We'll call this dat. So to store the directory of the files along with them, with their names. And now we have a whole bunch of different counties, housing data, all in these different CSVs, right? All these different data frames. So we could lapply over those and build linear models separately for each of the zip codes. What might be more useful, we might want to just go ahead and combine those into one big data frame. So let's do that. I'll demonstrate rbind and using the names of the files to specify within each data frame which file it came from. And then I'll stop.
So the structure of each of those CSVs is the same though, right? With
Yes.
the same column names? And,
Yes.
okay.
And if it weren't, then you would have to do some more involved data cleaning. So let's lapply over the data. Actually, let's apply over the file names. File. Call this E. So within this, so again, the way I like to write these is to use the example case of the first one. So file, oops, file, I'm going to set to file names 1. So there's my sheet. There's that. And then I'm going to add a column to that that is, what does this file look like? Okay. Well, we'll just call each the full file. We could do some text parsing and pull out just the zip code name, but in the interest of time, we will just say that dzip equals repeat file. We read the CSV, attach a column that will just be repeating the file name, and then we want to return the whole data frame. So now we have there's one empty file that it's not liking. What's that?
Oh, never mind.
No. You guys have heard of blackboard radiation? Have you heard of computer radiation? Everything's 10 times harder when there's somebody watching. Let's do this. If is null b return null, otherwise attach that. Why did it work before?
Couldn't you just set file to be like first 10 files?
Is one of the first 10. No, they don't all have the same structure. Some of them are empty. Anywho, so then in dat, so now we have a list of these and the zip code in each of the file names. So in the first one, it has that first zip code. In the second one, it has this second zip code. And then we can do call rbind dat. We'll call that prices. So now we have two values of zip and then all the other information. And so now we're off to the races, as they say. Clear?
So each of the CSV files had a whole, it wasn't just summary statistics in each one, it's actual observations.
Right.
Cool.
Cool.
Just gonna sit down and do it.
Yeah. And I think besides the poor organization of this talk, there are some useful idioms in here. So hopefully I'll leave this available, and hopefully it'll be useful as something to refer back to if you do want to R-bind or whatever.
And so S-apply is literally simplified L-apply?
Oh yeah. So S-apply does L-apply, and then it tries to simplify the results. So if everything is of the same data class, it will put them together into a vector or a matrix or an array, which can be dangerous. So we L-apply 125 function of x squared. That gives us back a list. If we S-apply, that simplifies them into a vector. Okay.
Thanks, Mike. That was really useful.
Thanks, yeah. There are a few other applies that are useful. Key apply stands for table apply. So at a So make a silly little data frame. If we key apply TF, the index is going to be GFX, and then we take the mean. Naturally. Oh. Yeah, Y. That goes through this data frame, tabulates by X, by the index that we gave it, and then does the function within each of those groups.
Gotcha.
It's kind of like the summarized functionality of dplyr.
Okay, so yeah, I just asked about S-apply because maybe you know this, but and like the first time I saw it was in Richard McElry's like statistical rethinking book, and I guess it's just because there's nowhere to get in trouble with the examples he used, and S-apply gives you back a vector, which is like a little bit more easy to operate on instead of getting L-apply on a list and then you got to do something else to that.
Yeah, and he uses them to create matrices sometimes that then work conveniently with his functions. But if you don't want a matrix of the particular shape that S-apply thinks you want, then you're better off using L-apply and then using do call R-bind or do call C-bind to put it into the structure you want.
Wait, so you get a matrix or a vector?
Or a higher dimensional array.
Oh, it depends on what you put in it.
Yeah. Or sometimes funky things. I once ran into a whole bunch of trouble because I was getting back like a matrix of data frames where each cell in the matrix was a data frame or something really goofy like that. So
It sounds like we're starting the broadcast.
there's also a function called vapply that does S-apply and then has a little check to make sure that it's returning the data type that you think you want. But I find in general, L-apply is easier to use and then just coerce it into whatever you want. Oh, one more useful thing is unlist. So if we unlist a list, it does the same thing as often what S-apply does. Takes each thing out of its train car and puts them into a vector. Cool. Yeah. Any questions from the ether? Okay. Signing off.